Hounan Chen and Professor Chandrasekhar, both of CSU. I'm with NOAA Physical Sciences Laboratory. So we have 8 talks today. 2 of those will be remote. The others are in person. And we're going to go ahead and kick things off with Lynn McMurdy, who's going to talk about impacts. So Lynn, take it away.
Good morning, everybody. Exciting to be here. And I'm going to talk about an ongoing field campaign impacts and investigation of microphysics and precipitation for Atlantic coast threatening snowstorms. As you all know, snowstorms and snowfall within them is highly variable. This variability makes challenges for forecasting and remote sensing of snowfall. You often see that, how do I make it first? There we go. That the snowfall is organized in narrow bands, and these are transitory sometimes, or sometimes they're very large and sit over one location for a long time. So the impacts field campaign is addressing these challenges. It's a Earth Venture Suborbital 3 field campaign to study East Coast snowstorms. Our goals are to characterize the spatial and temporal scales of snow bands, understand their dynamical, thermodynamics, and microphysics processes that control them, and apply this understanding to remote sensing and modeling. How are we going to do that? Well, we've been out in the field already for 2 years. We started in winter 2020, and then we had to skip a year due to COVID, and then we were there last year, and we have next deployment upcoming this winter. Our observational strategy relies on aircraft coordination. We have 2 aircraft. One is high above. Let's see if I can move this way. I can sort of lean towards. There we go. High above the storm systems, flying at 20 kilometers, the ER2, and it's a satellite simulating aircraft. It has remote sensing instrumentation, both passive and active, and the acronyms for the different instruments are listed here. You might recognize a few radars, LiDAR, and these 2 are radiometers. And then below, we have the P3 aircraft that's flying within the clouds themselves at various altitudes that we decide and control in real time while we're out there flying. And it has microphysical probes and flight level environmental measurements, such as a whole list of probes in the TAMS, the turbulent air motion system. And then when we're over water, we do dropsondes. So and we go and look for snowstorms. But when we are in the Northeast, we do have a couple of mobile trucks and also a stationary location that has a whole array of radar and radiometer and lots of different ground instrumentation. And as I speak, we have a second deployment in Connecticut. This first array of instrumentation is at Stony Brook, but the D3R, thanks to Chandra here, is being installed literally as I'm speaking right now in Connecticut. And we also use the New York Mesonet observations and have quite a large team of people doing on-demand sounding launches. So it's quite a array of instrumentation. This is a map of all the different flights we did just last year. So you can see we focused mostly in the Northeast, but if a storm of interest happened in the Midwest, I can't find my cursor. Please come back. Well, you can see that we also go there, or we go offshore if the storm of interest is there. So last year we had 11 science missions. 8 of them were well coordinated between the 2 aircraft. 3 of them were as well coordinated as we liked, because one reason or another, an aircraft had to go back early. A list of all our storms. I don't expect you to read this, but I am going to, because we are here in Chicago, show you some preliminary results for the one event that we flew over a deepening snowstorm last February 17th. So here we have some of our early results. On the left is MRMS composite radar reflectivity. And you can see that the region that we flew in over Illinois, I was just, wait, oh, there it's back. Okay, here we go. This line here is the flight track. And you see this very oblong shaped ellipse that highlights a region of higher reflectivity that we are identifying as a snow band. And the aircraft went right over the edge of it. We weren't allowed to go any closer to Chicago, obvious reasons. They're trying to land millions of planes, or mostly the planes were in the air trying to land, but they weren't allowed to land because there was snowfall rates of 25 millimeters an hour at Chicago Airport. So they weren't actually very happy that we were there, but they accommodated us. So on the middle panels here are radar reflectivity as measured from the HIRAP instrument on the ER2 looking downwards. And this, the one that we plotted here is the KU band. And the middle panel is the dual frequency ratio, or the KU minus KA. And then the bottom one is an estimate of vertical motion, where we took a CFAD profile of what the average vertical motions were and subtracted that out from the measured Doppler velocity to have an estimate of the actual vertical motion of the air. We're trying to take into account the fall velocity of the particles. It's kind of a rough estimate. So one thing that you notice here on go like that is a region of higher reflectivity that happens to be right where that snow band is. And that is a very strong enhancement in DFR, and in a region of more or less light snow vertical motions with some kind of interesting structure within that. So the P3 was flying underneath it, and that's what this horizontal line is here. The southeast side, you can see that there was a lot of drying, so we were kind of fighting the dry slot as we were flying there. But near that snow band, and actually within that snow band, we see that there was a really strong marked rise of a mean diameter of the particles that we were measuring. So this is a PSD and a DM plot with distance here. And so I'm circling where that snow band is. And so the mean diameter was a much bigger increase, and we had a lot fewer smaller particles. And using 3 different estimates of ice water content, you see that also is an enhancement of ice water content. So that is happening inside the band, but outside the band. So I'm now kind of focused on the earlier part of that leg. You see that not that much enhancement going on, but there was some interesting kind of little bursts of vertical motion in that region, and they're coincident with smaller particles. Again, some potential enhancement of ice water content, and we were hypothesizing that there was some lofting of supercooled droplets in that particular region at that time. Just to kind of show you that this enhancement within snow bands is not unique to that one storm that happened in Chicago. This is another event that we sampled in 2020, February 7th case. And now the snow band is highlighted in this, I lost the cursor again. Okay, you see that pink little, there we go. The pink oval. Don't get fooled by the parts to the east. That is high reflectivity due to a bright band, because this was an event that had rain to the east and snowing to the west. And it too was a region of enhanced reflectivity. Is a little harder to see with the scale we used, enhanced DFR in the red. And that was also larger particles. And this is some sample particle imagery here showing a lot more aggregation. And then outside the snow band, much smaller particles, some aggregation, but not as much. So you see that snow band really looked like in these 2 events, larger particles and more aggregation. So it's a multi-year field campaign. We're observing snow, and we're really looking forward to our last deployment. We have already sampled about 20 storm events in 2020 and 2022. And following my talk, you'll hear all kinds of results from those events. I want to just highlight, look, not only in this session, but there's some posters, so please go to them. There's already a BAMS article summarizing this, and also an IGAR summarizing the 2022. The DOIs are right there. We do have data sets that are posted to the DAC. Link here, contact me if you can't write it down fast enough or take a picture fast enough. Free to the public, please use it. Also, data workshop talks to learn more about the data. And we also have a field catalog for each deployment year. And just so you know, we are actually doing test flights literally right now. So I think the ER2 is going to take off maybe in a few hours and do a test flight for the instruments to make sure everything's working. And on Friday, we're going to do a P3 flight over Stony Brook, see what the coordination is with the ground network and calibration of the probes. So we're really will be ready for 23. So thank you, everybody. And I'm happy to answer questions. Thank you.
Any quick question for Lynn? Or you can save your question during the Q&A section.
Ask questions to the next people. Yeah.
So is this all DFR or DFRM? I've always been championing DFRM.
Yeah, we try to correct for attenuation.
So I will repeat, we tried to get the, so the person who did that was Joe Finland, who's coming up next, and he corrected for attenuation, and I didn't hear the rest. You can come over here, and since you're coming up next anyway, and answer Chandra's question.
No, I think he already answered. So-
Okay, good. Come on up. Yes.
Thanks, Lynn. Okay, so as Lynn mentioned, our next talk is from Joe Finland, who's going to talk more about impacts, comparison of precipitation structure and microphysical properties within two Alberta Clipper systems during the 2022 impacts deployment.
Great, thank you very much. So yeah, talking about a couple of systems that we sampled north of the border during the 2022 deployment. A little bit different from some of the classic nor'easters that you sometimes know and think about. But anyways, I'd like to acknowledge my co-authors who have been instrumental with feedback and collaborating with this project so far. Oh yeah, this one. Gosh. All right, so as I mentioned in the title, we were fortunate enough during the Impacts 2022 deployment to sample two Alberta Clippers in the Quebec region. And pictures to the right were taken by Stephen Nichols. He was on that flight flying above when we were flying above the storm, and also I think probably in it as the cloud was thinning. But anyways, Alberta Clippers can produce localized regions of significant snowfall on the ground, despite the fact that they may be fast movers. And this can present challenges for operational forecasting. But understanding the microphysical processes within these systems are instrumental to helping improve our numerical modeling and also our remote sensing retrieval. So the goals for this talk are to, first of all, compare the precip structures and microphysical properties between these clippers, and also to relate it back to how are they different, how are they similar to some of the other mid-latitude winter cyclones that we've sampled during the impacts 2020 and 2022. So Lynn's given an overview of the different airborne platforms. So for the stuff I'm focusing on regarding the P3, which is flying within these storms, information from the particle images themselves provide a nice qualitative look, but also derived particle size distributions and bulk microphysical properties from multiple probes are useful for understanding the properties associated with these storms. But also vertical motions from our TAMS instrument is also helpful to relate some of the vertical motions to these physical structures or the precipitation structures that are observed. And we also have our satellite simulating ER2 flying well above the storm, pictured here along with our Rockstar project lead, Lynn McMurdy, who was out there just last week, actually, in Palmdale, looking at the ER2 kind of implementation. So focusing for this talk on the HIRAP radar, which is a dual frequency radar. And in addition to radial velocity and spectrum width, we can leverage the difference between these reflectivities to employ neural network retrieval from Chase et al. To learn a little bit more about the mass weighted mean diameter, the normalized intercept parameter, and the ice water content in regions where we don't have in situ observations, because the P3 can't be everywhere at once. So that's very helpful. And then lastly, piggybacking on our sister project, Wintry Mix, which was operating in the Quebec area north of the St. Lawrence Valley. using data from two sites where our ER2 and P3 were doing coordinated flights over these two sites. And so for the interest of time today, I'll just be showing some results from the microrain radar at the Sorrel site. So I'll only be talking more in depth on one of our Alberta clippers for time today, but the January 19th system was a very interesting system. So we have an animation here of the MRMS composite reflectivity, and then we have these kind of like little snakes, which is our flight tracks from our ER2 and P3, flying right over the Sorrel site. So again, great co-located measurements there. But you could also see as we animate, there's kind of these filaments, regions of banded precipitation structures, maybe short-lived, but regions of higher reflectivity that can, of course, modulate the snowfall accumulation at the surface. And this was a pretty well-fronted genetic forced system, despite the fact that clippers tend to be known as having less moisture available to them. So just showing a couple of things with a particular flight leg on this day. The top left plot is estimated vertical velocities from the Ka band HIRAP radar. We try to use representative fall speeds binned by altitude, basically using a CFAT of radial velocity to back out our fall speeds and get a sense of the vertical motions within the system. And in this particular region where I have boxed in the black box, there was a region of downward motion, and you could see that in the top right panel with the TAMS 5-second average mean vertical velocity and also the standard deviation during this region. We had high variability in the vertical motions, and they're also kind of corroborating what our radar was showing with predominantly downward motion. Now, looking at the bottom left here, using the neural network retrieval, we could get a sense of the structure regarding the ice water content with the system. And in this box region, we encounter a fall streak with quite high ice water contents that's also corroborated by our in situ measurements from the P3 when we use the particle size distributions and back out the ice water content. So that's all interesting that it's, kind of fitting that mold there. And here are some representative particle images from a few of our probes showing the, planar crystals mixed in with some slightly larger aggregates. But just seconds earlier, just left of the black box, we had a huge rise in the mass weighted mean diameter where aggregation was more dominant. So there's a lot of variability within a short span within these Alberta Clipper systems. And it's kind of evident when you look at the precipitation structures inside. So looking a little bit farther down, this is the same flight leg. This is looking at the HIRAP Ka band radial velocity in the top left and spectrum width in the bottom left. And you can see that there's quite turbulent motions within the low level stable layer. And you could kind of see that in the oscillations in the radial velocity. And in the top left, there's overlaid her analysis of equivalent potential temperature, illustrating that stable layer. And on the right, just illustrating when we flew over the Sorrel MRR, we also see variability in the radial velocities and enhanced spectrum width that you see in the bottom right panel. So looking at high split back trajectories, we looked back to up 48 hours in the past, and this is kind of the pathways that these trajectories, kind of ended at along this our flight track, which mouse isn't working well, but along that our flight leg. And they originated about 3 or so kilometers and was descending into our stable later around 1.5 or so kilometers for this particular example. So stepping back and looking at things a little more statistically and comparing this and the February 19th Clipper system with all the other 9 mid-latitude cyclones where we had good co-located measurements between both the 2020 and 2022 deployments. And what you can see here as we bin it by temperature, a few takeaway points is with the 19 January Clipper system, mass weighted mean diameter was on average 24% higher. Normalized intercept parameter was 11% lower, and ice water content was lower. So we had less ice water content, but we also had some pretty appreciable aggregation occurring at some of these temperature ranges. And then looking at the February 19th Clipper system, DM, NW, and ice water content were all lower. This is part in fact because the depth of our cloud layer was quite lower with the second Alberta Clipper system. And then just kind of wrapping up, and I'll just kind of put all of these three up here. We've looked at the reflectivity profile between each Clipper system and also the other 9 mid-latitude cyclones for comparison. And so this is essentially a CFAT of KU band reflectivity. This is looking at the whole column now, the whole profile through these clouds. And a couple things to note is with our January 19 Clipper, the KU band reflectivity increases more rapidly in that -20 to -10 Celsius range. So a steeper slope in the reflectivity compared to the February Clipper and on average the other mid-latitude cyclones. And you can see in the center panel here, the February Clipper system had a narrower range in reflectivity and temperature, partially because just our system was shallower. And and then the last panel, just as a disclaimer, we ignored any columns where we had over our many cases where we had any bright banding, any melting of hydrometeors. So I'll just leave my 2 bullet points up here. I've kind of reiterated them a couple of times, but some future work is to further relate these radar observations and retrieve properties to ground-based measurements, and also relate the precipitation properties and clippers to snow bands. So yeah, just feel free to check out GitHub page. Me and Victoria McDonald, who was also a graduate student at UW, have done some work on simplifying our IO, like read routines and some processing routines related to the impacts data. So thank you.
We have time for a question for Joe. No question.
Audience, I have a question if the audience doesn't have. Oh, you go. Okay. So the DM and NW estimates you got, those were from the in situ probes, or are they like, did you ever do a check with how the retrievals work on?
Yeah, so was it the box and whisker plots?
Yeah.
Okay, so these data are valid where the P3 was flying. Now, you asked a question about the retrieval, correct? So there is a recent paper that we published looking at the 2020 deployment where we've compared the in situ DM and NW to the retrieval valid at the location where the P3 measurements were made. And overall, there were the results agreed quite well. This retrieval was trained on GPM-GB data, but with impacts, a lot of the results hold quite well. We're quite glad about it. So, yep. Did you have a question, or are we out of time?
I think we ought to just.
That's fine.
I'll ask you afterwards.
Yeah,
that's great. Great. Okay, I think our next 2 talks are virtual. The next one is by Chip Helms, and he's gonna.
Hi, I'm Chip Helms, and
Oh, all right. See, it is Chip. Okay, so Chip's going to talk about understanding the vertical slope of mesoscale snow bands, mesoscale snow band reflectivity signatures.
acknowledge my co-authors Jerry Heimsfield and Stephen Nichols, as well as the entire team behind the NASA Impacts Field Campaign, which collected a lot of the data that I'm going to be presenting here. So as the title says, I'm going to be focusing on the vertical slope of mesoscale snow band reflectivity signatures. And specifically, I'm going to be looking at this Midwest snowstorm case that occurred on the 5th of February of 2020. In this NextRad reflectivity mosaic, I've highlighted a number of these mesoscale snow bands, although for this talk, I'm just going to be focusing on this specific snow band. Now, one of the aircraft, the ER2, had an X-band radar on it called X-band, and that collected a nadir beam reflectivity curtain, which allows us to take a look at the vertical extent, sort of a vertical cross section. So I've circled the feature again here in red, and you can see that the vertical extent of this feature, it reaches up to around 7 kilometers or so. Now, in addition to this nadir beam, XRED also has a conically scanning beam, which means that we can take a cross-track slice, which is what we see on the left. And this is where you finally start to see this vertical slope that I'm referring to in the title. So the question comes up of what processes are responsible for the slope of this reflectivity feature. And what can these processes tell us about the formation and maintenance mechanisms of these banding features? So we came up with 5 possible causes of a sloped reflectivity signature. It could be isentropic upglide, potentially a fall streak mechanism, could be slantwise convection releasing symmetric instability. We could have some sort of a sloped dynamic feature that's enhancing precipitation. It could also be that this is an aggregation zone, and that zone is simply sloped due to perhaps a sloped temperature field. So for this talk, we're only going to focus on the first 3 of these potential causes. And we'll start off with isentropic flows. So on the left, I've overlaid the isentropes from the 3-kilometer HER analysis, and you can immediately see that they're pretty much flat. So that sort of eliminates the isentropic upglide as a potential cause. So we'll just cross that off and move on. So next up, we have fall streak mechanism. And this one's a little bit more complicated. We need to ask what snow fall speed would be needed for this feature to exist. So we can look to the slope as being the fall speed divided by the horizontal displacement rate by the shear. And this horizontal displacement rate can be computed as the product of the vertical shear and the thickness over which that vertical shear acts. If you plug stuff in and rearrange, we come up with that the required fall speed is the product between the slope, the vertical wind shear, and the thickness over which that vertical wind shear acts. So if we start plugging in numbers, we have a slope of around 24 meters per horizontal kilometer at the top of this feature, and at the bottom around 60 meters per kilometer. Because XRAD is conically scanning and has Doppler capabilities, we can perform a VAD wind retrieval and get a wind profile. From this wind profile, we've estimated that the average 2 to 4 kilometer along band vertical wind shear is around 7.8 meters per second per kilometer. And then as far as the thickness over which the shear acts, we can estimate that by the height difference along the slope. At the top of the feature, it's around 0.6 kilometers. At the bottom of the feature, it's about 1.5 kilometers. Plugging all of these in, we find that the required fall speed to produce this feature purely by fall streak mechanism would be at the top around 0.06 meters per second and at the bottom around 1.62 meters per second. Now that top fall speed is very slow for a falling snowflake, so that's probably not what's going on here, at least not purely. The bottom, however, is a reasonable snowflake fall speed, so it's plausible that this feature, at least the bottom slope of it, is the result of some sort of a fall streak mechanism. So moving on to slantwise convection, this is the release of symmetric instability. And just as a reminder, symmetric instability produces a situation where slantwise displacement will result in forces that push a parcel farther away from its initial position. And this is despite the fact that the environment can be stable to purely vertical or horizontal motion. Now, the vertical forces that are acting on this parcel are produced by buoyancy differences, and the horizontal forces are produced by momentum differences. And this is schematically illustrated over here on the left in a figure I've adapted from Bob House's Cloud Dynamics book. I've also included some useful references in case you also want to break off the rust on your symmetric instability knowledge. So let's apply this to our data. So here I have our XRAD nadir reflectivity curtain, and I've overlaid the HER analysis virtual potential temperature in purple and the geostrophic momentum in the dashed red. Also identified 6 regions that seemed of interest either in the reflectivity or in the HER fields. So when I do the displacement test to see whether there's symmetric instability or not, I find that 4 of these regions are symmetrically stable, but 2 of them have symmetric instability. Now, these 2 symmetrically unstable regions, unfortunately, don't seem to line up with the reflectivity features. However, they are both around 50 kilometers offset from the reflectivity features, which makes me wonder, is the analysis just off by 50 kilometers? I'm not sure, but it's something I'm digging into. Regardless of this, though, this can't explain the long band slope because it's in the wrong plane. but it does provide a formation and maintenance mechanism. So just to wrap things up, we looked at three possible causes for the slope reflectivity signature. We found that isentropic flow is almost certainly not responsible, at least in this case. The fall streak mechanism is plausible, especially for the bottom edge of the feature. And slantwise convection is possibly related to this feature, although not a cause for the slope, being more related in the way of being a formation and maintenance mechanism. So this leads us to our current working hypothesis that these bands are formed by slantwise convection and that the long band slope is produced as a fall streak, especially at the bottom edge. Now that top edge has a very shallow slope because of the ongoing release of symmetric instability continuing to produce additional particles at the top. I've also included a cross-section from a wharf simulation run we did, although I wasn't able to talk to it today. That is sort of the next area that our research is going in. And with that, if time and technology allows, I'll gladly take any questions. Thank you.
I think Chip is online. Do you have any question for him? Please, Lynn.
Hi, Chip. Great talk. And you and I can talk more later in the field. So I'm curious about your other two hypotheses that you didn't have a chance to deal with in the talk. How do you propose to do your aggregation? I can't remember how you phrased it, but the aggregation hypotheses.
So that's a good question. I feel like that should show up. I mean, for one, I could use model fields to look at, the temperature bands. But that might show up better, or that might also show up in some derived values from radar. That was one actually that just recently came to me. So I haven't had quite enough time to really flesh out the idea in my head. But yeah.
Okay, our next speaker is also in line from Mariko Au. I hope I'm pronouncing that correctly. Who's going to talk about characteristics of microscale updrafts and winter storms accompanying snow bands along the U.S. Northeast coast using high-resolution cloud radar observations.
Hello, my name is Mariko Owe of Stony Brook University. I'd like to talk about the characteristics of microscale updraft in snowstorms accompanying snow bands along the U.S. Northeast coast using high-resolution cloud radar observations. This study is funded by NSF and NASA Impact Field Campaign in collaboration between Stony Brook and North Carolina State University and Brookhaven National Lab. Snowband provides a heavy snowfall in U.S. Northeast coast every year. Many studies focused on synoptic and dynamical characteristics of snowband, such as front genesis, instability, mid-level trough. Some studies using high-resolution measurement recognized generating cells near the cloud top as an important source of snow in the winter storms, as you can see the right figures. However, there are still questions. What is the trigger of microscale updraft? What is the role of microscale updraft for snowband formations because of the still lack of the high spatial temporal observations? We investigated characteristics of microscale updraft and their relationships with mesoscale characteristics using cloud radar measurement. Stony Brook University operates Ka-band scanning polarimetric radar named Caspar in the middle of Long Island, New York. This has a full polarimetry, Doppler velocity, and Doppler spectral capabilities. This performed RHIs, PPI, and vertical pointing measurement every 7 minutes during the winter season. We selected 4 cases between the winter in 2017 and 2021. Right figure shows the storm tracks for the 4 cases. 3 of them provided multiple snowbands, providing heavy snowfall in the Long Island, and the other case had the only single band, showing the relatively smaller reflectivities compared to the others. This is showing the animation from Caspar RHI measurement for the case of February 1st, 2021. Top is reflectivity, middle is Doppler velocity, and bottom is spectrum width. Right animation is the next radar reflectivity from the lowest PPI measurement. Caspar RHIs revealed convective cells near the cloud tops in the moist neutral layers. These are consistent with the strong turbulence, as you can see in the Doppler velocity and the large spectrum width. These are the primary source of the heavy snowfalls. In addition to that, you can also see some intensification of radar reflectivity at the middle level of the storms. You also see the layers of large spectrum width consistent with the vertical wind shears shown in the Doppler velocities. We investigated the roles of the turbulence and updraft regions in the snowstorm. We detected updraft regions from Caspar vertical pointing measurement. First, we estimated hydrometeor sedimentations as the mean Doppler velocities, assuming that mean vertical air motion for a certain time period at a given height is almost 0. Top right figure showed the Doppler velocity versus reflectivities from all 4 cases. We estimated this kind of relationships every hour, every 500-meter height following Protat and Williams 2011. And then we picked up updraft regions as a corrected Doppler velocity greater than 0.4 meter per second. Top 3 plot shows the example result. Reflectivity, and middle is the Doppler velocity, measured Doppler velocity, and right is the detected updraft region. We detected many updraft regions associated with the generating cells near the cloud top, and also detected regions mid-level of the cloud. First, let's see how the updraft duration look like. The plot shows the distribution of updraft duration from 4 cases. You can see approximately logarithmic shape of the distribution, with most individual updraft in only a few seconds, less than 20 seconds. Considering the wind speed, and they are roughly equivalent to the spatial scales, less than 500 meters. 3 multi-band cases show the similar distribution, but one case with the single band showed the relatively smaller number of updraft regions. Where updraft regions were detected, this is height versus time cross-section of radar reflectivity by grayscale, and dot represent the updraft regions with colors showing the Doppler spectrum width. Right plot shows the histograms of the occurrence of updraft regions as time relative to the total cloudy time. Although there is a large variability among the cases, generally the updraft regions are found anytime, any height, regardless the snow band. This suggests that updraft regions can contribute to ice formation even outside the snowband. Updraft regions contribute to mass flux. Middle plot represents the mass flux estimated from the updraft regions. You can see the mass flux when the updraft regions tend to cluster near each other in space and time. The highest mass flux is produced associated with large spectrum width during the snowband period, as you can see the red dot during the snowband. There was some evidence the relationships between the updraft regions and wind shears. Bottom plot represent wind direction and contour represent vertical wind shears. A magenta line on the middle plot showed the moist Richardson number is some 0.25. You can see some detailed structure of the vertical wind shear within the storm. The highest mass flux is roughly consistent in time with low shear instability layers, suggesting that some triggers in the shear unstable layers. Summary, we investigated the characteristics of microscale updraft in the snowstorm using radar vertically pointing measurement. The distribution of updraft duration is approximately logarithmic with most individual updraft in only a few seconds. They are roughly equivalent to the spatial scales less than 500 meters. The updraft regions are found at all altitude and any time, regardless the snowband, suggesting that they can contribute to the precipitation mass growth, regardless the snowband. The updraft regions contributed to the upward mass flux when they cluster near each other in space and time, and subset of updraft regions with large spectrum widths produced large mass flux, roughly consistent in time and slightly above shear instability layers, suggesting some triggers in the shear unstable layers. That's all. Thank you for your attention. Hi, I'm taking any questions. Thank you.
Online.
All right. Okay, moving back to speakers in person. Our next talk is by Peter Breschner, who's going to talk about multimodal ice crystal size distributions in Atlantic coast snowstorms, results from impacts 2020. Come on, man.
All right. Hi, everyone. My name is Peter Breckner. I'm here to present to you all on the multimodal ice crystal size distributions in Atlantic coast snowstorms, results from impacts 2020. I would like to acknowledge the Impacts Field Campaign, the University of Oklahoma School of Meteorology, and the Cooperative Institute for Severe and High Impact Weather Research and Operations for helping organize and fund the field campaign. I'd also like to thank all my co-authors for helping me with my work. So my presentation deals with the February 7, 2020 case. As some of you may recall, the storm was up in the New England area, and the flight went through at 43 degrees north latitude between 78 and 74 degrees longitude. In the storm, convective regions were to the east and stratiform regions were to the west. And part of my work differentiates between the two regions. What I'm going to be showing you all today is stuff mainly about flight legs 1 and 5, which were both flown from west to east. The flights were generally flown from the higher altitudes for the flight leg 1 at around -15 Celsius to lower altitudes around -5 Celsius by the time we get to flight leg 5. So my work was on studying size distributions of ice particles in snowstorms. And part of my motivation was to eventually use my work to improve weather models and forecasts. I used a two-dimensional stereo probe and a high volume precipitation spectrometer to measure size distributions of ice crystals. The 2DS probe measures sizes that are below about 1 millimeter, while the HVPS-3 measures ice crystals larger than about 1 millimeter. And then I used the cloud droplet probe to make sure that the size distributions I was studying were ice crystal size distributions rather than liquid size distributions. So now I want to introduce you all to gamma distributions defined by n of d equals n naught d to the mu e to the minus lambda d. We use them for simplicity and integrability. The figure shown on the screen shows what happens when we change each of the parameters. I'm going to be introducing to you a fitting technique. So first I want to remind you all but any of you who may be unfamiliar with it, with the Farquhar et al. 2015 technique, which fits size distributions like the one shown using moments 0, 2, and 4. This particular size distribution was from leg 1, which was in the dendritic growth zone. And so on a previous field campaign, I developed a new methodology that is able to automatically detect the number of modes in the size distribution up to 3 modes, the least number necessary to fit the size distribution given the counting uncertainty. The methodology differentiates between unimodal, bimodal, and trimodal. And for bimodal distributions, it also differentiates based off of whether the split between the two modes occurs at a smaller or a larger diameter, as in B or C, respectively. What you see on the right here are the median size distributions normalized by ice water content for each type of size distribution as differentiated by my algorithm. You see unimodal in light blue, bimodal 1 in magenta, bimodal 2 in green, and trimodal in light orange. The unimodal in leg 1 with in the dendritic growth zone was primarily stratiform, but also had a fair amount of convective. Next most was bimodal 2, which was by and large convective. At the warmer temperature, at a higher temperature in the fifth leg, we see among ice crystal size distributions, they're all stratiform and they are bimodal 1, like what is shown in the figure on the screen. These have larger median mass diameter than the ones in the dendritic growth zone. Now I'm going to quickly introduce you all to volumes of equally realizable solutions, which illustrate the estimates for n naught, mu, and lambda with the uncertainty for each mode. It's easier to understand when we use the cross sections. So for unimodal size distributions in leg 1, we see as shown the approximate estimates for where the parameters are for convective in the top row, and stratiform in the bottom row, distributions with and not mu on the left, and not lambda in the center column, and mu lambda in the right column. You can also plot these cross-section ellipses for multimodal distributions such as trimodal distributions, as shown in this figure. And here are how the cross-section ellipses look for leg 5. These are all bimodal 1 because that's what leg 5 has. We see that we have a pretty significant distinction in lambda between the two modes, which we would expect. And since the bimodal 1 has a larger median mass diameter, it makes sense that the lambda would be smaller for the medium mode in these bimodal 1 distributions compared to the unimodal distributions from a previous slide. The main conclusions are that size distributions from impacts can be characterized using 3 distinct modes, and the stratiform bimodal 1 distributions are more common at the higher temperatures, while convective and the convective bimodal 2 and stratiform unimodal are more common in the dendritic growth zone. Right is a photo of the 2DS that I took when we were doing maintenance work in 2022. And I'm planning on doing some future work where I look into the ice crystal habits and try to connect those as best as I can with the modes using a methodology for measuring habits being developed by Julian. And that is my presentation. Any questions?
Question?
I have one actually. So Peter, maybe you already you addressed this and I missed it. How are you differentiating convective and stratiform precip?
Sure, let me go back to. Okay, yeah, so I differentiate between convective and stratiform by when in the flight leg it was I differentiate the same way it was differentiated in Barsi et al. 2022. Basically, it has to do with the longitude in the flight leg and corresponding to that the time during the flight leg.
Okay.
Quick question, Peter, I'm going to try this for other cases. Do you know
Yeah,
ones in mind?
Yeah, I do plan to try this in other cases. I'm still early in the work, so I wanted to do February 7th for this, but I'll try it with other cases too going forward.
Thank you. Great. Our next talk is from Pierre Kerstetter of the University of Oklahoma. Pierre is going to talk about the HORSE all-digital phased array weather system overview and first results.
Thank you. All right. Hello, everybody. Thank you for attending this presentation. I am presenting on behalf of Bob Palmer. So I'm not an engineer. Be gentle with me, please. But I want to acknowledge my co-authors. As you can see, this is a synergetic work between science and engineering. So first, I would like to start with some consideration on the weather radar development design and how science drives technical decisions. So the questions you want to ask when you design a phased array radar are, first, what is your scatterer? Will that be rain, snow, cloud particles? And what is the desired observation range? Because that will condition what kind of scattering you will get, the interaction between the radar wave and your scatterer, attenuation of the radar signal, sensitivity, and all these characteristics condition the wavelengths you want to use for your radar, the transmit power, and the antenna gain. Second question, is the observable scatterer geometrically complex almost all the time it is, especially hydrometeors, and that would push us toward polarimetry. Third question, within what we can, the range we can observe, what are the spatial scales of interest? What are the physical phenomena we want to resolve? And that will condition the spatial resolution we want, and that will condition, in terms of technology, the bandwidth and the antenna size. A bigger antenna, higher spatial resolution, but it is more costly. Also, a fine adaptive angular sampling, which differentiates mechanical and phased array. With phased array, we have more flexibility. And finally, along with spatial scale, we are to ask how fast are the atmospheric processes evolving. And there, the temporal resolution is key. So that will separate also mechanical radar, which is slower, versus a phased array radar. So if you combine the last two questions, we arrive at a conclusion that many atmospheric observational needs naturally lead toward a polarimetric phased array radar system. So here is a quick phased array radar research and development history. The vertical line corresponds to present time. And this is for ground-based systems, not spacebound. And as you can see, the trend is for more advanced capabilities and polarimetry. At this time, there is still much work to be done in order to get a meteorological quality phased array radar system. And it is probably the advanced technology demonstrator operated by NSSL is probably the closest system to reach that goal. But there is still much to do, and that implies synergistic work between science and engineering. Now, if you take the same systems and you group them by radar frequency, you see that they fall roughly into two categories, X-band and S-band. But for operational weather radar observations, S-band is the wavelength of choice because it is less attenuated. So now let's dive a bit into why are we targeting an all digital architecture? So here are shown from left to right various architectures, which with increasing capability and flexibility. What characterizes an all digital beamformer on the right is the fact that you can bring the digitization at as close as possible to each radiating element. So, okay, you can see my mouse, each radiating element here. With older architectures, we would use an analog beamformers. This older approach is simpler to implement, but it comes at a cost. It costs flexibility and capability. Now, with recent developments in the wireless communication industry, we are able to, again, bring digitization as close as possible and work at each radiating element level, which basically leads us to get a software-defined radar. What does it imply? It implies that you have increased capability and flexibility. You can meet needs corresponding to science priorities that cannot be met by other architectures. You can meet needs that will be designed by future science priorities. And if you think of it, if you have a network of radars like that, like 160, more than 160 radars in XRAD, you don't have to perform costly hardware upgrades. You can upgrade with a software upgrade, which is very fast. You can update your whole system and the network. All right, so now we have the architecture, we know the wavelengths, and we know that we want polarimetry. Where are we? So as of November 22, last month, here is what we have. The Horus system, you can see the photo, the center, you can see the radiating elements here on this panel. And on the left, you have the radome that is put on top of these radiating elements to make it weatherproof. So this is an S-band radar with polarimetric flexibility. You can see the values. We can do many things in terms of polarimetry. Well, I will pass. I won't go through all the characteristics, but it is around 20 kilowatts of peak power. This type of system is, you can see the aperture, right? So the size of the antenna. This is not the NextRad. NextRad is way bigger, but this is a demonstrator. It is highly scalable. And we can test all the advantages that I just mentioned in the previous slide, where we can design future applications, which makes here we have a future-proof radar, basically. So here are some of the first weather radar observations that were taken in May 22. At this time, we didn't have all of the radiating elements. So you can see on the top left, this is a vertical 5-panel array, vertically oriented. And that corresponds, so it means what? It means that in azimuth, you will have a fat beam, very low resolution, but in elevation, you will have a higher resolution. If you take a vertical cut in this plot here, you get the bottom panel, and you can see here an advantage of all digital technology. You can see how the side lobes and the negative elevation angles are lower than the upper lobes. And that is meant to mitigate ground clutter coming from these side lobes. So now if we run this data, you can see, well, those are not weather quality data yet. And I want to show you that because you can see all the tribulations and challenges that come along with designing a weather radar. So it's not there, we cannot use it yet for weather applications, but we have a way forward in order to reach that level. One big challenge I will mention is a multi-panel array calibration. You need all of the radiating elements to be synchronized in terms of phase. So for that, that task is pretty challenging. Here is how that was done at the time. You can see on the right constructive and destructive interferences between well, that we should not see that. But we can also, another thing is that we couldn't see these without an all digital architecture. So the next step is to use a near field scanner in January, February that will address this challenge. So I will go quickly here as a quick example. Also, during the summer, it was not raining much in Norman, so we used a plane as a scatterer to test the system. And we use the Horus in a configuration with very high range resolution and very high PRF. That may be useful for weather applications, but you can see here. So that is the flight plan that plane went over the arc several times. You can, well, I don't think you can see much about where the plane is in the sky, but you can see how the radar was able to follow it. So one thing that I want to highlight, finish, is that it is a very scalable system. And that is key because we will need higher angular resolution for weather applications. So you can see here on the left, the building blocks and how it is, the electronics associated with it. And each block here is one element on the antenna, which based on the scalability, we proposed already some concepts of bigger aperture, similar to NextRad, that would enable us to basically replace the current S-band NextRad data. So here are my takeaway points, and I will take almost Any question? And I will, those I cannot, I will defer to Bob.
Maybe a real quick question for Pierre.
I want to honor him with a question. This is not an engineering question. Why did you drop off C bands on the way?
Ah.
And, if you don't want to answer that, that's okay.
Well, S-band, well, attenuation with C, Norman, severe weather, C-band is attenuated, so they went for S-band.
No, the reason is throughout Europe and all over the world,
I know,
C band is the most sold radar now.
I know, yeah.
So anyway.
That's for, well, environmental reasons.
Awesome. All right, thanks, Pierre. Okay, the next talk is by Christopher Williams, University of Colorado. Christopher is going to talk about how much attenuation through a rain shaft extinguishes the signal from vertically pointing cloud radars.
Great, thank you. And I are an engineer, so I'm going to talk about, thank you conveners for letting me speak. And what I want to talk about is a problem that I came across, and I'm a little embarrassed that I didn't know about it, but then I made me look into it. And I then wanted to repeat this problem, be able to solve it with different radars. And so that's what I'm going to talk about. So here is a photograph of a DOE field campaign field site during the Go Amazon field campaign, which is in Manaus, Brazil. And I'm going to talk about data collected from the 1.2 gigahertz phased array radar wind profiler. It uses a phased array to either point vertically or off a few degrees to measure the horizontal wind. Then up on this shipping container, there is a W band 94 gigahertz radar. And I'm interested in looking at the evolution of raindrops as they fall. So I was looking at the radar wind profiler, Rayleigh scattering, reflectivity. I can see a bright band, and the dashed lines are just for your reference at 4 and 2 kilometer heights. And then looking at the 94 gigahertz W band vertically pointing radar, oh, there's a really great structure. I can probably look at some evolution of DSDs. And then I looked at the Parseval rain rate at the surface, and the rain rate was 0 or less than 1 millimeter per hour. And I'm like, oh, well, these are really nice, pretty pictures, but there's not much rain going on. And so then I said, let me flip this around and let me get some higher rain so I can look at breakup, coalescence, and rain. And here's the distrometer data, the surface rain rates above 10 millimeters per hour. And then I went and grabbed the radar data, and the radar wind profiler, the Rayleigh scattering, it was nice, had a nice bright band, there's convective rain, but then the W band was extinguished. There's no signal after so much distance. I'm like, oh. So I started looking at the literature, looking at my heroes, and like, how do you quantify how much attenuation is going through your rain shaft? So then looking at this high rain rates and the extinction, came up with this little model that could be repeated for any field site. And it's a little bit for me, but for other people too, that develop rain shafts that are just constant rain rate from the surface up to 4 kilometers. And each column is a different rain rate. And from each of these columns, you can simulate the measured reflectivity, which would be the effective reflectivity plus the attenuation. And I'll show you how I got these curves. These are good simulations, but radars don't measure reflectivity. They measure either the total power coming back or the signal to noise. If you don't have a calibrated radar, the radar wind profiler and other systems use signal to noise. Then once you have signal to noise, then that gets converted into reflectivity, which is the meteorological value that we're really interested in. So on the left-hand side are the figures that I showed before, showing the vertical cross sections. But at the profile at hour 16, the right-hand side shows what the W band is observing. And this is the Doppler velocity spectrum. So height is on the vertical axis, and then fall speed, radial downward motions on the right. If you look at the very top, you're seeing the noise level. And as you go lower in height, you actually have signal going above the noise. And you can see the me notch in the velocities. And so this is in signal to noise. And individual profiles are shown on the bottom. So here's the me notch. And then the signal to noise for this radar profile. So we have high reflective or high signal to noise at low range gates or close to the radar, and the signal to noise is decreasing. And then at about 0 dB signal to noise, this radar loses sensitivity. So there's no signal being detected. So for this radar, the threshold of 0 is going to be what's going to come back for our threshold. So the methodology is you define constant rain rate profiles, you develop a ZR relationship to convert rain into reflectivity. This would be unattenuated. Then to determine the attenuation, calculate KR relationships or specific attenuation relationships based on R. And then with range, you can get the path integrated attenuation. And that's the two-way path of the signal going out and back to the radar. With that information, you can then simulate the measured reflectivity, which is the effective reflectivity minus the path integrated attenuation. All of these are expressed in R. And then now we have to convert into signal to noise is what the radar is actually seeing. So you have a calibration constant, signal to noise is radar constant, the measured reflectivity, and then the R squared term for volume scattering. And so to make this repeatable and for everyone, I went to the pi-t matrix module to convert raindrop size distributions into scattering values. So I used the scattering calculations from pi-t matrix, calculated the backscattering extinction cross sections, and all the details are in this remote sensing paper. And from those scattering, you can calculate ZR relationships, KR relationships for different frequencies that are used in meteorological applications. And there's different plots of KR or KR and ZR. So given this information, you can construct your constant rain rate shafts on the left, create your attenuated reflectivity profiles, and these different lines are for different rain rates, and then convert that with the equation at the top into signal to noise. And for this particular radar, the minimum signal to noise was 0 dB. So that's our cutoff. So when the signal to noise drops to that value, then this particular radar can't see any further. It's complete. It's been complete. The signal's been completely extinguished. So the blue line is for a W band, this radar that was deployed in Go Amazon. And the horizontal axis is rain rate. And these are constant shafts of rain going up at these values, and then how high can you see into the shaft. So if you're at 25 millimeter per hour rain rate, this W band radar would see up to about 1.5 kilometers at different frequencies, given that the other radars have the same 0 dB threshold. A Ka band would see up to 2.5 kilometers. A K band or an MMR would see up to about 3.5 kilometers. And then depending on how you think, if you want to know how high to observe, if you want to observe up to 3 kilometers, and your rain rate must be less than this value for you to be able to observe through a constant rain rate shaft up to this height. And then just folding back into the observations, the top panel is the observations. The red is derived from the simulations, where the middle panel is constant rain rate shafts that were determined by the surface Percival rain rates. And so they're constant. So what you're seeing is the attenuated reflectivity at W band. And then the red dots are when that value goes across 0. So it's replicating what's being observed. And get some validation of what this is happening with this simple model. So while the high frequencies provide unique information, we have to understand the attenuation and when we'll be able to use the high frequencies for our studies. And so I wanted to provide a repeatable method that we can estimate the path length, because it's actually attenuation through a length that determines the attenuation. And this is all described in a paper in remote sensing. And then you have to remember, you have to determine the sensitivity for your radar to do these analyses. But once you have it, you'd have an idea of how far you can see through rain. And I'll leave it at that.
Question for Christopher? Pierre, can you please walk to the microphone?
Thank you, Chris. How do you, well, we still haven't solved the issue of the air motions to extract in order to estimate the particle size distribution, right?
Through the attenuation, I mean, or looking at patterns.
In general, when
general,
you want to estimate the PSD at a given altitude.
Okay, yep. Given a spectrum. Given the spectrum, estimate DSDs at each range gate.
Yes, and filter out the vertical motions that, the air motions that come to play and are integrated with the, yeah.
Okay, yeah, so I'm going to start with the W band because that's what's on the screen. And so the constraint here is that the mean scattering occurs at a 1.7 millimeter diameter raindrop. So that would be your lock, your key to do a vertical air motion with W band. So actually would fit the W band me fit.
Okay, thank you. We need to talk. I am interested.
Okay, but yeah, the lighter rain rates.
Okay, thank you, Christopher. All right, the last talk of the session is by Julia Shates. Am I pronouncing that right? Okay, great. The University of Wisconsin-Madison. And Julia's going to talk about multi-year analysis of rain snow levels at Marquette, Michigan.
Hi, everyone. So today I'll be talking to you about observations and results from a ground-based instrument suite in Marquette, Michigan. So just to start, the observations that we're looking at are of stratiform or cold rainfall, where we see snowfall forming aloft, snowflakes aggregating, encountering a melt layer, and then melting, becoming raindrops that reach the surface. And this we can also observe in ground-based observations such as radar. So that height where we see the snowflakes melting the rain, the melt level, has been shown to have a trend of increasing, that it's been shown that it's increasing with increasing surface warming. And that also results in an increase in precip intensity of rainfall at the surface. And in some places, we can see rainfall in the place of snowfall because of this. And this question of whether or not we're getting snow or rain at the surface or the phase discrimination is actually not straightforward. Using a temperature threshold is not necessarily effective because the surface temperature for where rain or snow occurs varies regionally. And so this plot is showing surface station data of where that 50% rain snow surface temperature threshold is. And there's a lot of spatial heterogeneity with that. The phase of precipitation is important for satellite retrievals of precipitation and brings us back to the need to use ground-based and satellite space-based radar observations to actually detect melting in the column. So for this work, I'm referring to the level where we see snow melting to rain as the rain snow level. And the observations I mentioned earlier that we're using are at Marquette, Michigan. So we have a ground-based instrument suite hosted at the National Weather Service office in Marquette, Michigan, where we've had observations being made since January 2014 and going forward. And for this work, we're looking at January 2014 to April 2020. So I have a photo here showing some of the instruments of the micro rain radar, which is our vertically profiling K-band radar, precipitation imaging package, which is our custom NASA video distrometer. And this site has been used for a few studies on snowfall as well. So the questions that we're asking on rain snow levels is how do the rain snow levels vary throughout the year? And what differences do we see in the macro and microphysical characteristics of rainfall as a function of that rain snow level? And then finally, how can these observations be coupled with ancillary measurements and reanalysis to better address uncertainties in retrievals of surface precipitation type? So first, let's take a look at some raw video footage from the PIP, the precipitation imaging package. So on the right, we have a video of snowfall, and on the left, we have rainfall. And some of the microphysical observations that we get from the PIP include the drop size distributions or particle size distributions for snow, the fall speeds of the snowflakes and raindrops, and then as well as that, the effective density and the rain rate and snow liquid water equivalents. Then we have the micro rain radar. So I have an example of a rain to snow transition event shown here. For both these plots, we have height on the y-axis, time on the x, and we're looking at radar reflectivity on the top panel and Doppler velocity on the bottom panel. And with this rain to snow transition event, we can see a clear bright band signature in the radar reflectivity. And in addition, we can see how different the Doppler velocity looks in the rain part of where we see really high Doppler velocity values as opposed to the snowfall. And we're going to use that information in order to detect where is it raining or snowing. So first, for our rain snow level identification, we need to have precipitation occurring. So we use a radar reflectivity threshold near the surface to determine that of -10 dBz. Then we use a Doppler velocity threshold to separate rain and snow near the surface. And then in order to identify the rain snow level, we're using the profiles of the Doppler velocities. So here are 2 separate minutes of Doppler velocity during the event. On the y-axis, we have the height above ground level. On the x-axis, we have Doppler velocity. And so we can see how the Doppler velocity changes with height during the rain part of the event. So we can see that's a sudden increase in the Doppler velocity associated with melting. So we're going to use that and use the gradient of the Doppler velocity to identify this sort of peak inflection of change. And that's how we identify our rain snow level. And using that method on this one particular case, this is how the results line up. We see how the rain snow level first matches up with the bright band and the radar reflectivity, and then clearly use the Doppler velocity to identify that rain snow level. So that's how it matches for the full event there. And then we take this method for our years of observations, and we get this distribution of rain snow levels for the many years. So I'm showing a box and whisker plot and 1/2 violin plots for the empirical distributions. And we have the height on the above ground level on the y-axis, and each box is for each of the months. And we can see the spread of the rain snow levels and height. Also, we can only see up to 3 kilometers above ground level because that's the operating range height of the radar. So while in the summer months, we could have higher observations of rain snow levels, we're not observing them using the MRR. So some of the key results that answer our first question that I brought up earlier is how they vary throughout the year, as we see those higher rain snow levels in the summer, lower rain snow levels in the winter. And in fall and spring, we're seeing that the rain snow levels span the entire range of the height of the radar. So one of the key observations that comes up from this distribution is that many of the observations fall within what's known as a satellite radar blind zone, where ground clutter could be obscuring a satellite radar's ability to detect melting near the surface. Next, our second question is, what differences do we see in the macro and microphysical characteristics of rainfall as a function of the rain snow level? And so in order to do this, we separate the rain snow levels into 4 separate height categories just to be able to compare what is it, how do they look at different heights? How are the microphysical characteristics different? So let's take a look at some PIP observations. So in here, I'm showing a mean drop size distribution where we have the log 10 DSD concentration on the y-axis, and then on the x-axis, we have the drop diameter. And we can see, and each one of the lines is for a different height category. So we can see that for higher rain snow level, so above 1.8 kilometers above ground level, we see a higher number of small drops. And then for rain snow levels that occur below 1.8 kilometers, there are a higher number of larger hydrometeors observed by the PIP. Then we can take a look at the mean fall speeds observed by the PIP, where now on the y-axis, we have the fall speeds. So what really stands out in the fall speed here is that for lower rain snow levels, we see a lower fall speed for the same size equivalent drop diameter. And this could be indicative of possibly mixed phase precipitation observed by the PIP for these lower rain snow levels. And in addition to the fact we see a higher number of larger hydrometeors, this sort of supports that as well. Then from the PIP, we can get rain rates. And so now here on the y-axis, I have our counts, and on the x-axis, I have rain rates. So we see a higher, for higher rain snow levels, higher rain rates, and that's consistent with what we'd expect with a higher melt level, more intense precipitation. And I don't have time to show this in a plot today, but we also looked at the near surface MRR reflectivity values and compared those to the PIP. And we see a higher concentration of larger MRR reflectivity values in addition to those higher PIP rain rates. So then for our final question, how can these observations be coupled with ancillary measurements and reanalyses to better address uncertainties in retrievals of surface precipitation type? So in order to do this, we compared our MRR rain snow levels to reanalysis derived melt levels. And so using both ERA5 and MERA2 reanalysis, we use the wet bulb temperature isotherm at 0 degrees Celsius to define that reanalysis melt level. So for this one plot, showing generally good agreement between the MRR rain snow levels and the reanalysis melt levels. But we're seeing that the melt levels are occurring above the MRR rain snow levels, which would make sense because it takes some time for snowflakes to melt. And in addition, we looked at the wet bulb temperature isotherm at 0.5 degrees Celsius, as well as 1 degree Celsius, and seeing good agreement between those reanalysis melt level heights and the MRR rain snow levels, particularly at 1 degree Celsius. So with that, I will leave up the questions and the summarized key takeaways from those questions up on the screen, and I'm happy to take questions.
Any questions for Julia?
Hey, Julia, nice talk. Out of curiosity, how many actual cases of rain do you have December, January, February, Marquette, for your statistics?
Right, so we have, that's a great question. I don't have the exact number of minutes in my head at the moment. Definitely every single winter, there's multiple cases in those, for that span of the time period. It's a great question. I would love to tell you a more specific answer, so maybe we can talk right after.
I would love to. Thanks.
Dean?
Great talk. I really enjoyed it. I was struck by your example, and we saw this frequently during impacts where you have, when it's raining, you have a melting level height somewhere 1.5, 2 kilometers, and then it just plummets to the surface. There's no sloping of that melting level height. It's like one, or it's almost like a step jump. So do you have any thoughts? I think that's something we would like to investigate more ourselves, but any thoughts about why it's just, there's no like steady erosion of that melting level? It's just like somebody flipped a switch and we were suddenly sowing.
Yeah, that's a great question. I'm not sure at the moment what could cause that sort of jump in the melt level to suddenly seeing snowfall. For that particular event, we actually did see a little bit of mixed phase precipitation as well. So that event is a little different maybe than, yeah. Thanks for your question. Thank you.
Okay. We have 3 minutes for Q&A. We have about 25 people online. Any questions from the online attendees? You can raise your hand or you can put your question in the chat. Okay. If you have any question for any of the speakers, this is a good time to bring that up. Everybody hungry?
Nobody's hungry. I actually have a question for Joe. I didn't get a chance to ask earlier, but you mentioned these, large gradients in particle size distributions. Does that have anything to do with topography? I don't know what the topography is in the area you were sampling, but I'm just curious. You might want to.
Yeah, that's a good question. That's something I should look at a little bit more. I don't believe the topography was very impressive in that region, but that's something that we could definitely take a look at and see if that's modulating the microphysics above that. So good question.
Okay, any other questions? If not, let's thank all the speakers for some really interesting talks today. And this afternoon, we have a follow-up poster session starting at 2:45.
Yeah.
I think it's, I forget the number. It's 35 to, I can't remember. Anyway, look it up. It's a follow-on for this. We had an online poster session this morning. It went really well. So this will be a nice complement to that. So thanks everyone again for attending, and look forward to seeing you this afternoon.